Thank you very much for attending today's webinar. We're discussing today how to interface Python and R trading strategies with MetaTrader 4 using ZeroMQ, which is a messaging and concurrency framework. I'll go on to describe what ZeroMQ is and how the ZeroMQ universe can be employed in connecting external trading strategies to MetaTrader 4. In terms of prerequisites, it is assumed today that attendees have some programming experience in Python, R, and particularly MQL, as we'll need all three to create this distributed trading system that we're going to talk about today. Knowledge of TCP socket communication is not mandatory, but is definitely a big plus. If you do have knowledge of TCP socket communication, that is great. If you don't, however, you can follow along with the slides and notes today, and it's probably something that you would need to read up on and implement or practice after the webinar is over, should you wish to implement the example system that we're proposing today. Knowledge of MQL is a plus, of course, particularly functions in MQL expert advisors such as initialization, deinitialization, timing, and tick-wise data collection. Those include on-init, on-dinit, on-tick, and particularly on-timer, as that's the function that we'll be demonstrating how to repetitively get data across the various different components of the distributed trading system we'll be talking about today. In terms of agenda, firstly, we'll begin with a brief description on the reasoning behind this webinar, why we're holding it, what prompted it, and the technologies herein, discuss those in detail. We'll go on to propose one kind of distributed trading system, one of many different proposals that we could have done today. It's by no means a mandatory design. It is flexible, and that's the whole idea behind this presentation, is to demonstrate what are the tools, the components that you would need to implement a system whereby you can write trading strategies outside of MetaTrader 4 and have them interface with MetaTrader 4 in a number of ways. We'll go on to discuss what ZeroMQ is in terms of its features, its functionality. Why would we use it for this distributed trading system if our goal is to connect trading strategies outside MetaTrader 4 to MetaTrader 4? We'll discuss the system architecture for something like this, talk about communication patterns that are presented by ZeroMQ, talk about the components we'll need in a MetaTrader 4 expert advisor to be able to complete the picture. Trading strategies outside MetaTrader 4, communicating with MetaTrader 4. We'll go on to describe the implementation of our proposed system, couple it with some sample code that we'll go through, showing you the various bits of code that were used in implementing this. And finally, we'll conclude with a Q&A where I encourage you to ask any questions that you've had during the webinar at that time. So let's begin. In terms of introduction, why we're holding this webinar, I will get to shortly. We're presenting a technique today that employs ZeroMQ. ZeroMQ is an open source asynchronous messaging library and concurrency framework, and it will help us it's used for building a communications bridge between external trading strategies and MetaTrader 4. Please bear in mind that the focus today is on R and Python when connecting to MetaTrader 4 with ZeroMQ. But as you'll see shortly in future slides, ZeroMQ has a very large repository of supported programming languages that can be used. So you could be developing your strategies in Java, for instance, or C++, or C#, or Node.js, or PHP, Perl, etc. They all have bindings. They all have respective bindings with ZeroMQ and can be used to communicate with MetaTrader 4, because MQL4 is also a ZeroMQ supported language. In terms of the reasoning behind this webinar, firstly, there is a lack of comprehensive, publicly available literature about this topic, connecting external programming languages to MetaTrader 4. So that was one major reason for us to go ahead and publish blog posts about this and also hold this webinar describing the implementation in detail. Secondly, the second two reasons are more along the lines of fall into the category of maintenance overhead. So traders have traditionally relied on WinSock and WinAPI based solutions that often require frequent revision with Microsoft and MetaQuotes updates. So the maintenance overhead with those solutions is high. Thirdly, any alternatives to ZeroMQ, they include named pipes and other approaches where file system dependent functionality forms the bridge between MetaTrader and external programming languages. So again, there's the maintenance overhead issue there. So all in all, we have two major reasons. Firstly, there's the lack of information that talks about this, describes this in detail. There are several sort of mini tutorials written by people experimenting with ZeroMQ and MetaTrader 4, but there's nothing comprehensive, no major article or no major tutorial about this or description anywhere that takes you from step 1 to step X or step A to Z. So those two being the main reasons behind this webinar being held today and the blog post that was published prior to this. As we talk about the distributed trading system, we'll discuss ZeroMQ in more detail. Once again, I'd like to reiterate that the proposed system here is just one of many different implementations that you could come up with. It totally depends on your particular requirements. The idea behind the distributed trading system we're proposing today is just one of many that you could implement. Our proposed system should consist of one or more trading strategies developed outside of MetaTrader 4, that is in non-MQL languages. So again, that could be Python, R, C++, C#, Java, and a number of other languages supported by ZeroMQ. Our proposed distributed trading system should also use MetaTrader 4 for acquiring market data, for trade execution, and for management of those trades. So supporting multiple non-MQL strategies, interfacing with MetaTrader 4 simultaneously would be another requirement. It should consider each trading strategy as an independent client connecting to it. I must add that here we're assuming that MetaTrader 4 will act as the server receiving commands, instructions from trading strategies outside its universe, and therefore treating those instances as clients and acting as the server. It should consider MetaTrader 4 as the server, as I just said, and the medium to market, the bridge to market. And finally, it should permit both server and clients to communicate with each other on demand. So this means that a trading strategy, for example, that's attempting to execute commands on the server taking trades to market, for instance, should be able to retrieve information about those trades, get notifications about success or failure of executions, get bid-ask rates for symbols, get historical data for symbols, all through the server as well, through MetaTrader 4. So there should be bidirectional communication. And this proposed distributed trading system would therefore look something like this in a very simple world, and in a very simplistic way. The MetaTrader 4 server acts as the nucleus with all your various trading strategies, infinite in number as far as the resources are available. As long as the resources are available, multiple trading strategies connecting to MetaTrader 4 that is behaving in this example as the server, while the strategies themselves are behaving as clients. Now, what is ZeroMQ? We've talked a lot about ZeroMQ, so let's discuss what it actually is and why we are using it for this implementation. ZeroMQ as a framework enables programmers to connect any code to any other code, and it does this in a number of ways. It eliminates a MetaTrader user's dependency on just MetaTrader supported technology. So one problem that traders could have with programming backgrounds that don't include MQL is that they've been trading with, say, a strategy written in Python or R for an extended period of time, and to trade on the foreign exchange market, they come across a venue where MetaTrader 4 is the means to market. That therefore means that in order to develop systems for MetaTrader 4, you would need to know MQL. So that is essentially a problem that ZeroMQ eliminates, because what they can then do is, by writing appropriate code within their existing systems that permits the use of ZeroMQ to connect to MetaTrader 4, they can then have an EA written that supports ZeroMQ communication, or figure out a way to write into ZeroMQ EA. They won't need to figure anything out after this webinar today, because we're going to give you sample code to achieve that. A template on how to write an MQL expert advisor that incorporates ZeroMQ. So those problems are what ZeroMQ helps us eliminate. External programming languages connecting to MetaTrader 4 from outside the MQL environment. Traders can therefore develop indicators and strategies in C, C#, C++, Python, R, Java, and any other ZeroMQ supported language, and deploy those strategies to market via MetaTrader 4, but not coding the strategy in MetaTrader 4. And this has several other advantages as well, because MetaTrader has its own supported features, its own supported indicators, language constructs, libraries, etc., that traders are with external programming backgrounds are therefore freed from. You no longer have to rely on those features, indicators, and constructs in order to execute your strategies via MetaTrader 4. ZeroMQ also, in terms of machine learning, you can leverage machine learning toolkits in Python and R for complex data analysis. That's otherwise not possible in MQL, because MQL has no known machine learning libraries nor infrastructure to deal with machine learning. And they can leverage these toolkits in external languages like Python and R while interfacing with MetaTrader 4 for trade execution and management. And ZeroMQ can therefore be used as a high-performance transport layer in sophisticated distributed trading systems that are otherwise, as I mentioned, very difficult to implement in MQL, if at all. Different strategy components, much like different strategies connecting to one server, those strategies being clients connecting to MT4 as the server in this example, different components of one trading strategy could also be written in different programming languages if required, and seamlessly talk to each other over TCP, inter-process, in-process, or multicast communication protocols. And ZeroMQ makes implementation of those protocols very simple, because it has its own communication patterns that allow traders with programming backgrounds to do more high-level programming, as I'll explain shortly, instead of dealing with the low-level, slightly lower-level infrastructure, defining, for example, socket I/O, working with that, making sure it's robust, error-free, etc. Its multiple communication patterns and disconnected operation enables programmers, traders with programming backgrounds to achieve that. The three main communication patterns that simplify this socket-based communication are reprec, which is request and reply, publish and subscribe, push and pull. And as you'll see further on in this webinar, we'll be using the request, reply, and push and pull communication patterns for our proposed implementation today. ZeroMQ supports several programming languages, as I've mentioned throughout this webinar, even though we focus on Python and R today. And the sample code that you'll be provided towards the latter half of this webinar will be in Python and R, and MQL, of course, for the MetaTrader 4 Expert Advisor. If you are programming strategies and currently working with them in other programming languages, check the ZeroMQ bindings list here on zeromq.org/bindings:_start, the URL displayed at the bottom of this slide. And you'll see at least 2 pages worth of supported programming languages in the ZeroMQ universe, some of those being Python, R, Java, C, C#, Node.js, PHP, Perl, Ruby, Scala, and more. Excuse me. Now, moving on to planning the system architecture for implementing this distributed trading system. ZeroMQ enables servers and clients, as I mentioned, to connect to each other on demand, particularly useful for designing distributed trading infrastructure. And why this is particularly useful is because it takes away the lower level hurdles in socket communication. ZeroMQ therefore allows you to flexibly change components in your system. You could, for example, you could build a system in a way, you could have trading strategies that can act as both clients and servers, or can be clients or servers. And at any given time, they can communicate with each other in either of those two or both of those two capacities. So that's this flexibility is very welcome in the trading world, because it allows you to flex a bit in terms of design and communicate more efficiently and easily in some ways, because if you've developed something, you've developed a trading strategy that is client only, you could in future perhaps do something about that in terms of making the trading strategy act as a client in some respects for some functions, but act as a server in other functions, taking instructions from other trading strategies. To make that a bit simpler, for example, you can have a trading strategy that is, say, written in Python, where there's a risk management component of this trading strategy that is written in R. So you could have this trading strategy be both a client and a server, where it's a server to the other strategy accepting instructions from it for risk management decisions, but it's a client to the MetaTrader 4 where it's sending commands to MetaTrader 4 for onwards execution to the market. In that way, ZeroMQ assists with easily implementing such design patterns. ZeroMQ also supports several communication patterns that I've just discussed that permit higher level data transfer, and most importantly, it frees programmers to focus more on the transfer logic, as we just talked about in that example, where we could have a strategy that gets its, for example, risk management component from an R system, another component from a Java system, another component from a C++ system, all three of those components connecting as clients to the Python trading strategy, which is a server to those components, but a client to MetaTrader 4. So ZeroMQ permits that sort of programming to be achieved. Now, a bit more on the communication patterns that we've been talking about. I'll go on to show you an infographic on what this system, this particular distributed trading system, this example we're presenting today would look like, and the communication patterns that we'll be using. So we'll be using a request reply. The three main available to us are request reply, publish, subscribe, and push pull. In our example, we'll be using request reply and push pull only. MetaTrader 4 in this example will be our server, and the trading strategy will be our client. As I've mentioned before, this is not a must, and you will need to decide on whatever flow control suits you best. Here's an infographic that we put together on what such a system would look like. On the right-hand side, you have your trading strategy, which in this example is a ZeroMQ client application. We have two types of sockets. The request reply socket above, which is a two-way socket, which means you can send instructions to MetaTrader 4, the ZeroMQ server, and you can also accept responses from that server. Towards the bottom half, we have a push-pull socket, which is a one-way socket, whereby the trading strategy can pull data from the server that, for instance, is not critical. In this example, we're going to use the request reply socket for critical command execution, for example, trades, open a trade, modify a trade, close a trade, things like that. Whereas with non-critical things, for example, getting trade history, if it's not part of executing further trades, it's non-critical information, and therefore we've chosen in this example to use a completely separate socket for those sorts of purposes. The key difference between the request reply socket and the push-pull socket is that request reply is bidirectional, and push-pull in this is unidirectional or one-way. And we'll go on to describe this implementation here shortly. So the infographic shows you a trading strategy on the right-hand side that communicates with a MetaTrader 4 expert advisor, which we will implement as a ZeroMQ server application. It will accept commands via those two sockets. It will communicate with the trading strategy via those two sockets, and it will have three components of its own: a message router, a message parser, and an interpreter and executor. So these three modules we'll go on to describe here in a little bit of detail to give you an idea of what you would need to do to implement them. And the great news is that once we're done with explaining them, the sample code we're providing you gives you a template to expand on. So we'll give you code in MQL that implements the message router, the message parser, interpreter, and executor to allow you to basically expand those based on what your requirements are. So let's describe the request reply pattern in a little bit of detail. The server in our example here is a MetaTrader 4 expert advisor, and it will employ a TCP socket of type reply to receive requests and to send responses. And a rep socket must always initiate a pair of calls. It must first execute a receive call, whereby it gets information from the client, and it should always follow that up with a send call to send information back to the client to complete that exchange. The client, the trading strategy, for example in Python, will employ a TCP socket of type rec, which is request, to send requests and receive responses. A rec socket must always initiate a pair of calls too, so it must first do a send, followed by a receive to complete the exchange. For this implementation, the request reply pattern will enable our clients to send commands to the MetaTrader 4 server, the clients being the external trading strategies, for example in Python or Java or C++, and for our clients to then receive acknowledgements of the same. So for instance, your trading strategy could want to open a trade on the market. You could therefore send an open, modify, or close trade command. You could ask for bid-ask rates for a particular symbol. You could want historical prices for a symbol. You could want currently executing trades currently in execution. You could you may want to request a history of trades already executed in the past over a certain time frame. All of those things can be done using this pattern, request and reply. And again, just to show you where that fits in the scheme we've just seen, the request reply socket is the two-way socket at the top, in the top half of this infographic, where the trading strategy is going to communicate with the ZeroMQ server, the MetaTrader 4 Expert Advisor, for critical instructions, such as trading, getting real-time information, and things like that. The push-pull pattern is our non-critical pattern in this example. The server, the MetaTrader 4 Expert Advisor, will also employ a second push socket to send additional information to clients. In our example here, the clients are the trading strategies. This is a one-way socket, and the server will only be able to send data to this socket, so without being able to receive anything back. That's where the non-critical component comes in. So because we've chosen the push-pull socket for this particular function, because if the server has to send something to the client, the trading strategy, where it's not so important or quote-unquote life-threatening in a way, then the server can afford to send that information reliably and not expect anything in return. The client, the trading strategy, again, will also employ a second pull socket so that the push-pull exchange is completed. It will need to implement the pull socket to receive additional information from the server. Again, if all of this is a lot to take in, please note that we are going to provide you sample code at the end of this webinar on our GitHub profile. We've uploaded it there already for you, but we need to get to the sample code so I can describe where these communication patterns are implemented, and then I encourage you to download those samples and play around with them and expand them as you see fit per your own requirements. More on the push-pull socket. It's a one-way socket. The pull socket is also a one-way socket, and the client will only be able to receive data from the socket without being able to send anything back. The push-pull pattern, therefore, enables servers and clients to exchange data with each other on demand, but in one direction only, without expecting a response. And you could, of course, have swapped this out. We don't need to use a push-pull communication pattern here. We may well have used a second request-reply pattern. It totally depends on your particular application's requirements, your own decisions on application flow control. Again, I'm repeatedly showing the infographic so we can, as we digest more content, we can see where it fits in our system visually. We can visualize this. It always helps to understand this material a lot better. So once again, the trading strategy on the right-hand side in this example is a ZeroMQ client. It is communicating via two sockets with our server, the MetaTrader 4 Expert Advisor. The job of the Expert Advisor is to take our instructions, and if they are trading instructions, to take them to market. If they are information instructions, to get that information from the market and send it back to our trading strategy on the right. For critical items, such as trade executions, we will be using the request reply socket in this example, of which there are many. So your example could use the request reply socket in a completely different capacity. I must reiterate that this example uses these sockets in this fashion only. There are plenty of ways you could do this. And in this example, again, the push-pull socket is used for getting non-critical information where the server can afford to send the information reliably, but not necessarily expect a response from the client. So in summary, our proposed architecture here, in our proposed architecture, the server will employ two sockets, one of type reply and another of type push. And our client, the trading strategy written in an external programming language like Python or R or C++, will employ two sockets as well. It will implement a request socket and a pull socket, as we've just described. And finally, one more look at the infographic to put all of this into place. On the right-hand side, once again, we have the trading strategy. We have the two sockets in the middle, request and reply for critical things, push and pull for non-critical things, both of them allowing us to communicate, do data exchange with our server, that in this example is the MetaTrader 4 Expert Advisor. The MetaTrader 4 Expert Advisor is therefore the bridge between this trading strategy and the market. Any commands executed via the trading strategy on the server will be taken to market. If they're successful, the trading strategy will be informed through one of those sockets depending on the nature of the information. So if it's a trade failure, it makes sense for you to route that information through the request reply socket, keeping things critical and non-critical. If it's just bit-ask data that doesn't need to be taken into consideration immediately, or just things like in the fix API world of heartbeats, or looking for trade context related information that is non-critical in terms of time, you could use the push-pull socket in this implementation for that purpose. Finally, we get to the components we've been seeing in this MetaTrader 4 Expert Advisor scheme. So the message router, the parser, the interpreter, and the executor. These components need implementation too. And the three main modules are, firstly, the router, the message router. This allows the Expert Advisor to receive commands from the trading strategy, the external trading strategy, and send acknowledgements back for connecting clients through the reply socket. The router processes all the messages on to the parser, and it is the parser's job to take those messages received and decompose them into actions for the next module, which is the interpreter and executor. The interpreter and executor literally interprets the decomposed messages and performs the requested actions accordingly. So for example, if your client is requesting market data, the module gathers it from the MetaTrader 4 history database and sends it onto the client via the push socket. Again, in this example, we're using the push socket, but if it's critical information that is time sensitive, you may choose to have it sent back through the request reply implementation. Alternatively, if the client is requesting a buy or a sell trade, for example, to be opened on the Euro USD, it sends the trade to market and a result notification to the client via the push socket, if it's non-critical, through the request reply pattern, if it's critical. And again, in this example, your example may treat this completely differently. And here we are once again with this infographic where I'm repeatedly showing it so we can make sense of all the material we're digesting. Trading strategy on the right, MetaTrader 4 Expert Advisor on the left. The strategy is the client. The Expert Advisor is the server. Both implement ZeroMQ. Both communicate with each other through these two sockets and are taken to market and back as a result. In terms of implementation and sample code, the fun bit for which we needed all of this theory, and hopefully the infographic was helpful in digesting the theory and the concepts. You will need the following for implementation. Firstly, ZeroMQ itself. Now, here's where we need to be specific. So ZeroMQ has MQL4 bindings as well. If you're going to implement a server in MetaTrader 4, you will naturally need a ZeroMQ implementation in there. To be able to do so, you'll need an MQL4 binding, which is essentially a library that allows you to write code inside MQL4 that allows you to implement the server actions that we've just been describing. In Python, you'll need the PyZMQ package. In R, you'll need the RZMQ package. If you're implementing in Java, then the ZeroMQ library. And if you're implementing in C++, there is more than one library for that. Multiple libraries are available on the zeromq.org bindings page for CPP. If you visit this link at the bottom, zeromq.org/bindings:CPP, that will show you a fairly lengthy list of C++ supported ZeroMQ bindings. To give you a head start, we've published a functional expert advisor with the full implementation that's been discussed in this webinar today, all the way from message router, parser, to interpreter and executor. The MQL sample code provided it's quite extensible, as I've been mentioning throughout the webinar, and can be used as a template in your efforts. Again, it helps you understand the structure of the code. If you feel you need to rewrite the thing, that's absolutely fine. The idea is to demonstrate how to implement the ZeroMQ interface in MetaTrader 4 as well as in your own programming languages if they are supported by ZeroMQ, which more than likely they are. Sample code is available on this link that we're going to skip to now when we get to our web browser. I'll show you what the code looks like, and we'll go through the code and I'll describe to you each component that we've discussed in this presentation today. The sample code is available on our GitHub page, github.com/Darwinex/Darwinex Labs, and there we've uploaded a template for a ZeroMQ enabled MT4 expert advisor that I will proceed to show you now, and we'll cut through the code to quickly see which component is implemented where and how, what libraries you need, etc. And we've also got an example 0MQ client written in R and an example 0MQ client written in Python, also on the GitHub page. So before we get to the Q&A, we're going to skip over to the web browser, where could you please confirm, I'm just quickly going to change my screen so we can see just the web browser so it's a bit more clear. Could I please get a yes or a no from someone in the audience that you can see the web browser clearly, that we're on the GitHub page? Could one of you please just put in a yes in the questions box? Fantastic, thank you. Okay, great. So here we are on the GitHub page, github.com/Darwinex/Darwinex Labs. And over here, if you proceed to Tools, and under Tools, you'll see we've got directories for different programming languages for different bits of research that we do. Under MQL4 is where you'll find the template EA. If we open up the EA and just scroll through the code, I can quickly demonstrate how the message router, the parser, the interpreter, and executor have been implemented. Firstly, could I please ask you to confirm if this screen resolution is okay for you? Can you see the code clearly? Could one of you please confirm? Are you able to read the code? Or alternatively, you could follow the code along separately in your own browser window. Oh, you can. Okay, great. Thank you for that. Right, so you'll notice include ZMQ/ZMQ.MQH. This is the header file you'll need. We're using, there are several implementations of MQL, of 0MQ and MQL. The one we've chosen for this implementation is on github.com/DINGMAOTU. This is in the source code here on GitHub, so you can copy this link and go to it. Follow the instructions to install this library for use inside MetaTrader 4. It's very, very easy. In fact, that was the main reason we chose this one, because it's the easiest to implement out of the few options you have. Some constants that have been described here, the ports to use for binding to, for the reply socket, the push socket, etc. in this example. Remember, this is in our example today, in this presentation, we've assumed that the MetaTrader 4 Expert Advisor is the server. Therefore, we've implemented the reply socket and the push socket. On init function, you'll notice we're using an event millisecond timer, and you could set this to pretty much anything. We've chosen 1 millisecond, which is very, very, very frequent. It will essentially run any commands inside the initialization function at that frequency. We bind to the ports we've specified, and we continue to set a few other options. Set linger is the maximum amount of time in milliseconds that the thread will try to send messages after its socket has been closed. And set high watermark, send high watermark is if we initiate a send without having a corresponding socket draining the queue or accepting those sends, then we'll be eating up memory as the socket just keeps enqueuing messages. So this allows you to specify how many messages at maximum you should send before waiting. How many messages do we want to buffer in RAM before blocking the socket? DINIT essentially unbinds us from the ports that we've used for the reply socket and the push socket. On timer is where the interpretation, the routing, interpreting, and the rest of it, parsing and interpreting happens. In this particular example, you'll notice a function called message handler, and this message handler takes your request that's inbound from your trading strategy and does a few things with it. The example here uses a class ZMQ-MSG to deliver the message back to the calling function. You construct a reply if the size is greater than 0, as in does the communication have anything in it? If yes, then parse the message, interpret the message, and respond to the connecting strategy that yes, we are processing the entry. Again, this is a template, so you can use this template to expand on the logic here. This has been written specifically to demonstrate where the routing, parsing, interpreting happens. Again, moving on to the interpretation, interpret ZMQ message is the function that takes the input and the socket and then does a few things with it depending on the action. We've also provided some comments here for what sort of message formats you could use, structures of messages that you could then parse and interpret accordingly. So here are some examples. You don't have to use them. These are assumed to be sent over the connection in raw format. You may choose to use some form of encryption down the line, so that's entirely up to you. This example assumes raw strings are being exchanged between the trading strategy as well as the server and the server. More proposed messaging formats in case, for example, if you wanted your trading strategy that is written in, say, Python, to retrieve rates for a particular symbol, the bid-ask rates for a symbol, you could use this format, send this message structure to the server EA. The server EA would then implement how to deal with such a message further down in the code. Again, this code has been written for demonstration purposes. There are more efficient ways of running this sequence of ifs, especially if you have a large number of commands that your application could process. So you are not at all compelled to follow this scheme of running if command after if command. The idea here was to demonstrate how to go about attempting to retrieve and parse and interpret messages. A little switch block here has been written for you, whereby you can see how you would go about interpreting and responding appropriately depending on the message. Informing the pull client, sending messages back through the one-way socket, sending messages back through the one-way socket as well as through the normal socket, etc. And the parsing happens here where, depending on how you've defined your input structure for the message, for example, data, symbol, time frame, start time, end time, your parse function would be responsible for dissecting that message and converting it into an array that can then be processed by your interpreter function. And then, if it needs execution, to execute it. And more sample functions here at the bottom for you to show you how to go about getting those bid-ask rates, for example, and sending those bid-ask rates or any other data you'd like to the push socket so that it can be sent forward to the client trading strategy that is expecting it in the pull socket if it's requested it. Right, so this is the MQL template to give you an idea of how you could start implementing a server in using ZeroMQ inside MetaTrader 4. If we go back to tools, there are some basic clients written for you in Python and R. So ZeroMQ MT4 Python template, some implementations of the message structures we discussed here are displayed here too, so you can go through this code in your own time, and it shows you how to do the reverse. It shows you what a client would be doing in connecting to this MetaTrader 4 Expert Advisor. Similarly for R, we've done one in R2, and the R file is called ZeroMQ MT4R template. So here you'll see an example written in R to perform both the Python and R template files perform exactly the same functions that as each other. So they do not perform any actual trade execution or anything like that. They're developed in a manner that will allow you to expand on them if you're writing your trading strategies in Python and R. Examples at this point in time have not been provided for any other programming languages. However, if they do surface, if we do write them, we'll update you about those and, of course, upload them to GitHub as well. So moving back to my PowerPoint screen. Right, so that concludes our webinar for the day. And hopefully you've enjoyed the content and it's been useful. There's been a lot to take in, all the way from socket communication to understanding how to go about implementing them. Please do visit the GitHub profile when you have time. Go through the sample code provided and come up with ways to expand that code, particularly if it's important for you to keep your trading strategies in the languages that they are already written in and not have to write them entirely in MQL, if it's even possible to rewrite them in MQL. Several Darwins on the exchange do currently use this architecture. So there are Darwins that are powered by Python and R, as well as C++ components in a trading strategy, and then ZeroMQ is used as the transport layer between those strategies and MetaTrader 4. So if you're one of those people who would like to go ahead and be able to trade through MetaTrader 4 without having to rewrite your trading strategy in MQL, hopefully this webinar has been useful to help you understand how that can be achieved, provided your programming language is supported by ZeroMQ, the messaging and concurrency framework that we've talked about today. Thank you very much for your time, and I'd like to invite you to ask any questions you may have had during this webinar, and please go ahead now. I have a question here on are there libraries in C++ for ZeroMQ? Yes, there are. During the webinar, we talked about C++ being the one language where there are multiple implementations of ZeroMQ. So if you visit the ZeroMQ bindings C++ section, you will find these. You will find a number of C++ libraries of varying flavors and complexities. So yes, there definitely are libraries, and it really boils down to what your end goals are and what you'd like to implement and how flexible your system needs to be. And the libraries that are available attend to pretty much several different patterns of design. So go ahead and check those out on the ZeroMQ bindings website. Any other questions? We have another question here about communication patterns. Why use push-pull when you can do everything through request-reply? That's a perfectly valid question. There's nothing wrong with that at all. As I mentioned during this presentation, that in this particular example, we've tried to demonstrate the use of multiple communication patterns between ZeroMQ, your trading strategy, and MetaTrader 4. We decided, for demonstration's sake, to use a request-reply pattern for critical decisions, critical instruction exchange, and a push-pull pattern for non-critical instruction exchange. So what you just said makes complete sense. You could just use one socket in this case, in this very simplistic case, for achieving both, and there's absolutely nothing wrong with that. So valid question, and hopefully that's answered it. And yes, you don't need another pattern if you can do with the existing one you already have. But remember that this implementation has been a very basic example. The idea is to sort of educate attendees on what's possible and how complex you can make your distributed trading architecture even with MetaTrader 4 if you involve ZeroMQ. Any further questions? No? Well, hopefully this has been good for you, and the content has been easy to digest. I appreciate we've done quite a lot today, and hopefully the infographics coupled with sample code that I hope you'll be perusing later as well has helped you understand this implementation. And if you have any ideas for other implementations, or if you run into any sort of quizzical moments where you're trying to decide on an appropriate architecture or things like that, if you'd like our feedback, we're always here. Please write info@darwinex.com with any questions to do with the contents of this webinar today, and we'd be happy to respond with feedback as soon as possible. And always share ideas as much as you can. The more you share, the more answers you get, the more concerns get mitigated, and the more we grow in this world of intercommunicatedness. That is not a word. But thank you very much for your time, and hope to see you again very soon. Take care. Have a good evening.